Ladies and gentlemen, meine Damen und Herren, I wish you on my behalf also most welcome to this event and the esoteric title we have picked up. A little bit about background, why this title was chosen. I think many of you have read the book Hitchhiker's Guide to the Galaxy by Douglas Adams. And there he introduced the answer to the ultimate question, being 42. Well, it has been ever since a kind of, among the geeks, a kind of thing where they think about where it ever comes from. And when there was a 10th anniversary of Douglas Adams' death, there was a book written where they had collected a number of things. Why 42? So I picked up some of them. There are a long list of things. But first of all, Douglas Adams said that it was a joke. It had to be a number, an ordinary, smallest number, and I chose that one. Binary representation, base 13. Tibetan monks are all complete nonsense. I sat on my desk, stared into the garden, and thought 42 will do. I typed it out, end of story. Well, anyway, throughout the history, various numbers have had special meaning ascribed to them. For example, Plato called the study of number symbolism the highest level of knowledge, while Pythagoras believed numbers had souls as well as magical powers. So pick up what the geeks had thought. Why 42? Well, the first one in the list is Queen Victoria's husband, Prince Albert, died at the age of 42. They had 42 grandchildren, and their great-grandson, Edward VIII, abdicated at the age of 42. Well, there's another one which I pick up. There is a long list, but anyway, Elvis Presley died at the age of 42. Okay, since Douglas Adams was a British author, of course, there was another reason, people thought. Cricket has 42 laws. Okay, let me go back to this joke. Anyway, the human quest to understand the complexities of life, the universe, and everything, it is not a joke, but kind of everlasting endeavor we have. I would like to pick up a thought of Egon Schiele, the great Austrian artist. When he was asked, what do you think about modern art? And he answered, art is not modern, art is eternal. I like to think in the same way about science. It is a kind of eternal endeavor. So what is the question then? If the answer is 42, what is the question? The ultimate question, indeed. Well, we are interested in human behavior and networks and human sociality altogether. So I would like to pick up a thought from Robin Dunbar, anthropologist from Oxford. In his book, in Human Evolution, he was asking what makes us uniquely human. And he answered, our capability of telling stories. For that, we of course need a language. So the quest indeed is more or less to understand the social complexity. Social complexity, what it entails communication, exchange of norms, values, ideas, and social and cultural resources in a system which we call network. Okay, let me now move on to introduce our speaker who is going to answer a number of these questions. Professor Geoffrey West is a theoretical physicist, a former president and distinguished professor of the Santa Fe Institute.
I have something I have to say at the beginning. Slightly embarrassed that I didn't quite appreciate what the time limitations were for the talk. So my talk is too long for the allotted time. So what I'm going to do is I'll try to flip through some slides, and you'll just have to bear with me as I try to fit it in. And you'll be the commander-in-chief, and we'll, please. So I got this somewhat pretentious title, but it was in response a little bit to Kimmo's bizarre title for the whole thing. And you'll see that I do have a question at the end. It's implied already in this. It's the future of the planet, of course, is the ultimate question. But the future of the planet in terms of socioeconomic activity, of course, us. And I also have, as you will see, some suggestions for not 42, but for other numbers that maybe play the role of 42. So I'm a physicist by training. I spent most of my career doing high-energy physics, quarks and gluons and string theory and dark matter and so on. And I started working on some similar questions, analogous questions in biology. So this talk is very much taken from a physicist viewpoint, but someone that has spent quite a lot of time thinking about biology, and more recently about social systems, as was intimated in the title, such as cities, urbanization, the question of companies, and just the whole question of long-term global sustainability. And I think the starting point for me is the recognition that everybody is very familiar with the idea that we live in an exponentially expanding universe, Hubble constant and all the other stuff. But very few people recognize explicitly, even though they sort of know it implicitly, that actually we live in an exponentially expanding socioeconomic universe, actually faster than exponential. So here's numbers. This is the United States, because that's what I know best, is that the US population 200 years ago, at the beginning of the Industrial Revolution, was just 4% urban. It's now well over 80% urban. The world passed the halfway mark just a few years ago and is heading towards that 70 to 80% level during some part towards the end of this century. And this is kind of astonishing, especially if you just put it into some simple numbers. This is equivalent, if you just average, to urbanizing at the rate of well over 1 million, actually do the numbers, like 1.4 million people every week, which is equivalent to adding a New York metropolitan area, something the size of approximately 50 million people, every 2 months from now to mid-century. And that's equivalent to adding everything you see around you here every 2 weeks. Vienna, every 2 weeks, is coming on this planet inextricably. Now, that is unbelievable. It's hard to believe that we're going to sustain that. Or where is it all going to come from? So that's the issue that I'm going to be talking about. Some other numbers that go along with it is China, of course, was slow to urbanize, but just passed the halfway mark recently and is heading towards the 70, 80%. That's the urban, and the red is the urban, the yellow is rural. If one had been able to take a photograph of the planet from a satellite the year I was born, which is a very long time ago, by the way, that's what it would look like. Well, especially you can't see anything because there's the light here. But if you look at it, there's actually something on here. That's what it looks like now. So in that my short little life, the planet is just not only lit up, it's burnt up. And, you know, this is just some obvious example that's clear that there must be something like global warming. And of course, that's reflected in this. This is the population growth. I was born here when it was just over 2 billion people. They're now 7.5 billion. And that's just unbelievable. It's just been straight up. So, you know, this is the real issue we should all be dealing with as far as I'm concerned. And it's been driven by urbanization, and we have to ask where that came from. So that is, of course, again reflected in the paradigm that we have adopted, the extraordinary discovery that we made a couple of hundred years ago of fossil fuels and the development of entrepreneurship and of capitalism. This has been an amazing discovery that has led to all the marvelous things that are around us. We wouldn't have any of it without any of that. And that's fantastic. But it is that, of course, this has led to the growth of cities. But the point that I'm going to emphasize is the whole future of the planet is actually a reflection of what happens in our cities. And so understanding cities is crucial. So here's what we mean by cities. Everybody recognizes a city. It comes in different shapes and forms. And we also sort of qualitatively understand why people are drawn to cities. There's material well-being, greater opportunity, more cultural life, a sexier, buzzier life kind of thing, more fancy restaurants, good education, blah, 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 et cetera, et cetera. And I will elaborate on this shortly. But of course, from a physicist's viewpoint, as distinct, by the way, from an economist's viewpoint, none of this can exist without this, energy. Everything ultimately has to be driven by energy. And you don't have to be a physicist to know that if you transform energy, because the most fundamental law of the universe is the second law of thermodynamics, if you transform energy, then you produce entropy. You produce random pollution, if you like. And so this necessarily, in producing our socioeconomic system, we produce socioeconomic entropy, which means phenomena like this, and this, and this, and this, all of which you recognize, and this, and of course this. And no doubt, much of the social unrest around the globe is caused by this pressure and this exponential expansion, faster than exponential expansion we've been undergoing. And we're going to see, I would speculate, much, much more of this as the system continues to accelerate. And the question is, and this is the question, is that what Vienna will look like in 20, 50, or 100 years? Or those nice pictures we saw? Or in particular, is that what London is going to look like soon, or not? Just to make it provocative. So we need to understand cities, I believe, and the phenomenon of urbanization. And one of the problems is that when you think of cities, you just look out here, you immediately think, oh, Vienna, all those marvelous Baroque buildings and palaces and all that, you know, marvelous, those boulevards. You think of Paris and its boulevards, or New York and the skyscrapers. And of course, that is a city, but that's the uninteresting part of the city. The interesting part of the city are everybody in this room, are people. That's what's interesting about a city, is that it is the people that are the city, and it is the dynamic among those people that leads to all of this. So that's going to be fundamental. So this is what a city is, of course, is the interaction between the infrastructure and the dynamic of the people interacting among themselves and with the infrastructure. Or this is a nice picture, because there in the background is the infrastructure that's been there for 2,000 years. And here's the people, And people have been doing this effectively for 2,000 years, sitting around bullshitting all kinds of, and this, of course, is what creates ideas, innovation, and wealth. Doing this in some form or another, and the whole point of a city is it's a machine for facilitating that interaction, okay? It's the greatest, maybe it's the greatest invention we've had since we've stopped being hunter-gatherers. So there it is, or this, here's New York City, 120 years ago, and you can viscerally feel the primitive forms of idea creation and entrepreneurship and trying to get on in the world and so on. Those buildings, again, are still there, different people, but they're doing the same thing. Doesn't look like this anymore. But inside those buildings, all those people are doing effectively what's going on here, okay, in business and so forth. So the other thing that you get from this, if you want to try to understand it as a science or as a physicist, is that you have to integrate the infrastructure, energy, resources, so to speak, metabolism of the city, the physicality of the city, with the information content that's being exchanged between human beings, creating all of this. In biology, it might be the genomics, but that's where innovation and wealth is created. So just to go back to what I said, cities and urbanization, on the one hand, the problem, because all of the problems we face, from global warming, or climate change at least, climate change to questions of financial stability, to questions of pollution and, pardon me, of health, disease, poverty, and so on, are all basically generated by cities and urbanization, because that's where the people are. But they're also the solution, because cities have this extraordinary magnetic effect of sucking people in. All the smart people end up in cities. All the ideas and wealth basically have been and will continue to be made in cities. So it's both sides of the coin. And so this, again, to emphasize that we need to have asked the question, is it conceivable to develop a quantitative predictive science of cities in the sense that a physicist thinks of? That's, of course, a daunting problem and probably impossible, but let's see what progress we can make. First thing to recognize is that the way we generally deal with them, and this goes to something about the idea of having a complexity hub, is that, first of all, we make boxes of everything. This is the way we deal with things, typically. We put all these in boxes, and in fact, within those boxes, there are more boxes. So we don't sort of have people dealing very much with health issues or the AIDS problem or whatever, Zika viruses, interacting with financiers, thinking about the future of the stock market, or and so on, or the questions of pollution. These are all dealt with, you know, the whole emphasis on the question of global warming. Marvelous. But if you only think of global warming, not realizing that all of these things are each one itself a complex, adaptive, evolving system, but the whole thing together is integrated into a complex, adaptive system, I think is crucial. So that's my little introduction, and now I'm going to take a tangent and talk a little bit about biology, and then I'm going to come back to this question. The first thing is that if there is to be any science underlying this, in the sense that I'm thinking of anyway, quantitative, predictive, analytic, mathematizable, computational, it's not going to be Newton's laws kind of science. It's going to be much more coarse-grained, very low resolution. You can't, you're not going to be able to predict things in great detail. You can't predict. It's not conceivable that you can predict the future of Vienna with a bunch of equations. Even, by the way, with, you're a computational scientist, with I don't care how much fucking AI goes into it, you're not going to be able to predict the future of a city. But the question is, to what extent can we understand it and get understand the underlying dynamics and principles? So I'm going to switch gears to biology and ask a bunch of coarse-grained questions about life. So here's one. Why is it that I can say, for example, everybody in this room is going to be dead, and many of us much before 100 years. In 100 years' time, none of you will be here, and in much less than that, some of us won't be here. When the hell does that 100 years come from? Why isn't it that we're not all dead already? And by the way, if you had been living 500 years ago, we would all be dead by now, unless you were some of you probably have aristocratic origins. I certainly don't. I would certainly have been dead. So where does that 100 years, and why not 1,000 years? Why can't we live for 1,000,000 years? And where does it come from in our genes and so on? So what the hell happened between this and this? So that's a coarse-grained question. And similarly, why is it that everybody had to sleep of the order of 8 hours last night and tonight, and not 15 hours like a mouse, or 3 hours like an elephant, or 2 hours like a whale? Why? Where in the hell does 8 hours? Why 8 hours? Why, in fact, do we have to sleep at all? Okay, and so on, other questions. And going back to the socioeconomic, asking, of course, what I'm going to imply is that cities and companies have something in common with organisms. They certainly do. We think, in fact, all of those, I consider them bullshit books about companies, about, they talk about the DNA of the company and the metabolism of the marketplace, I don't know, whatever. So the question is, are these substantial statements, or are they just metaphors? And indeed, one question, which has always intrigued me, is why is it that essentially all companies die and almost no cities do? Of course, you can think of ancient cities that do, but I do remind you that you can drop an atom bomb on a city and 25 years later it's fine. All you have to do is twiddle the stock market by a little bit and you lose a TWA or a General Motors, etc. So cities are unbelievably resilient and companies are extraordinarily fragile. Okay, so let's talk about us. This is mammals. We range from, this is the smallest, 2 grams, to something very large you're familiar with. That little thing there is the size of a shrew on the scale of an elephant, and that there is the elephant on the size of a blue whale. This is us as a mammal, and we're one of these. And of course, we believe that each one of these organisms, not just mammals, but everything around us is evolved by natural selection, process of evolution, and that each subcomponent, each organ, each cell type, each genome has evolved uniquely, has a unique history, it's historically contingent. A lot of accidents happened, and a lot of competition happened that led to this. So there's this image of natural selection being random. There's a kind of randomness out there that is part of it. Therefore, if you were to ask about how the characteristics of these organisms change with their size, you would expect, if you just plotted things, some variable versus their size, and plotted them on a graph, they'd be all over the graph because the points would represent the historical contingency reflecting this evolutionary process. Well, it turns out that's completely untrue. That's not at all what happens. And here's the most fundamental process for everything I'm talking about, which is metabolism. How do you take stuff and make it into life, or make stuff, make it into companies or economies? That's metabolic rate, and that's plotted on the y-axis. On the horizontal axis is size, and it's plotted logarithmically, so I can get, meaning going up by factors of 10, in order to get a mouse and an elephant on the same graph. If I make this up, but if I tried to put the shrew and the whale on this graph on a linear plot, I remind you, and if I put the shrew here at the bottom of the plot, and I were to put the whale, it would end up in Bratislava somewhere. So you have no choice but to plot it this way, actually. But here's what's extraordinary. They all line up pretty much on the same line. That's already amazing that there's a tremendous regularity in what we perceive of as a highly complex evolving process with randomness associated with it. Furthermore, the slope of this line has this curious number very close to 3/4. Namely that, so it's not, I mean, what you might, at the most naive level, if you didn't know about evolution or anything, you would say, well, you double the size, you double the number of cells, you therefore double the metabolic rate. You need twice as much energy to support twice as many cells. Should be linear. That's the sort of simplistic answer. It's not, it's 3/4, which means there's an extraordinary economy of scale the bigger you get. The bigger you get, every time you double the size, very approximately, you get 25% savings. We are much more efficient than your dog, but much less efficient than your horse, roughly, by a predictable amount. So there's this extraordinary economy of scale, but it turns out anything that you can measure about organisms across any kind of taxonomic group has the same behavior, same kind of behavior. And here's a mundane one. This is heart rate, and there's, again, you see a very systematic behavior. The slope of that is -1/4, minus because it's decreasing. Here's what you think of as yourself, your white to gray matter in your brain, and it's very close to 5/4. And here's something with much more variance in it, but the statistical fit also gives rise to a slope of very close to 1/4. And this is the genome length versus size for a bunch of unicells. And I could show you for the rest of the afternoon 50 more or 75 more of these graphs, and they all look the same, plotted this way, and they all have not the number 42, but the number 4 dominates everything. 4 is the number that controls all of the life around you in this coarse-grained way, everything. So there it is, that's what it says there, that's called quarter-power scaling. Just to give you an example, there's a lot of variance in this, but I just want to do, I don't know what the tech, anyway, it doesn't matter. This is lifespan, how long you live versus size, and that symbolically means if you plotted it in the way I did it, it would have a slope of +1/4. That's the data. That's the data. There's a lot of variance in it. I don't want to go into that, but here's the point I want to make. Heart rate, I just showed, decreases with 1/4. Therefore, if I multiply them together, the increase of lifespan is exactly compensated by the decrease of heart rate. So heart rate times lifespan doesn't change with size. It's an invariant. But what is heart rate times lifespan? It's the number of heartbeats in a lifetime. There's the data. Doesn't change from a tiny animal to a big one. I mean, there's variance, of course, but it's approximately the same. We all have about 1.5 billion heartbeats in our life, all meaning all mammals that have ever existed, including essentially all, on the average, including all human beings until about 1850. And beginning in 1850, because of the Industrial Revolution, and what's going to be pretty much, in a moment, the rest of the talk, because we urbanized. And I will come back to that. So what is the reason for this? So there's a whole theory underlying this, which I have no time to talk about, but it is that the origin of all these scaling laws is the physics and mathematics of the networks that distribute energy in particular, but also information. And it is the structure of those networks, and you can work it. I'm not, as I say, I have no time to talk about it here, but it's these. I just show you pictures of networks, and it is that the universality of these networks at different levels. That's what you look like on your inside, but on the bottom right is the inside of a cell, for example, in terms of the network structure. I'm not going to go into that. Suffice it to say that there's a complete theory for working out where all these scaling laws come from, including the number 4, where the number 4 comes from. And if there's time, I can say a few more words about it. But I want to move on, and I want to, before going to the cities, back to socioeconomic, I want to talk about growth, because that's crucial in socioeconomic systems. In biology, here's how it works. You know how it works. You eat, you metabolize, you send metabolic energy, so to speak, through your networks to the cells. At the cellular level, oops, I forgot to put that on there, yes. At the cellular level, it maintains what's there, it repairs cells, and then adds new ones to the ones that have died, and then adds new growth if you're in a growing phase. And you can put this into mathematics using the networks and so on. I'm, again, not doing that. And if you do it, you can get a mathematical formula for how any organism grows. And here's an example. And by the way, that theory has universal parameters. So there's the prediction of the theory. Those are the data points. That's for a rat. And the important point I want to emphasize here is that the sublinear scaling, the 3/4, the economy of scale, leads to bounded growth, it turns out, in the theory. That's why you stop growing. So you grow quickly and stop growing, and the theory explains why you stop growing. And here it is for a bunch. That happens to be a very good fit. Here's some other data on many others, all, by the way, with the same fundamental parameters. So there's kind of universal theory of growth. And you can see that it's universal because, and I don't have time to explain this, the theory tells you that instead of plotting size versus age, it tells you what variable you should be plotting that's rescaled in some clever way derived, driven by the theory to plot on this axis versus this axis so that everybody grows in the same way. There's a universal growth no matter what size you are, and this is just some small number of animals that we showed for this. So, I just want to summarize this. We have these really extraordinary nonlinear scaling laws that have this universal quarter power. They express an economy of scale. The bigger you are, the less you need per cell to stay alive. I didn't emphasize this, but the bigger you are, the slower the pace of life. Heart rate slow down, oxygen diffusion is slow, and so on. Everything slows down the bigger you are. Growth is sigmoidal, meaning it stops, and you have a finite lifespan. It stops, and then you die. So that's the kind of summary, the big summary of basically all the life around us. And all of it can be explained by these networks. And of course, this is great. This is wonderful, but it's a terrible, if it were true, that social systems had this would be considered terrible. Growth stops. So let's now take this idea and take the same paradigm and apply it now to cities and companies. I probably won't have time to talk about companies. Let's see. So the first question is, are they scaled versions of one another? We saw that despite the whale living in the ocean and the giraffe having a long neck and the elephant a trunk and we walk on two legs and mice scurry around, we're actually at kind of this coarse-grained level of 80–90% scaled versions of one another in terms of anything we can measure in a non-linear way with this magic number 1/4 playing a role derived from the network theory. I'll use America, New York, just a scaled up Los Angeles, which is a scaled up Chicago, which is a scaled up Santa Fe, which is a small town where I live, despite the fact that they have different histories, geographies, and cultures. They look quite different. On the other hand, of course, we recognize them all as cities, and we also recognize that cities, like biological systems, are networked. They have physical networks. They have roads and transport systems, of course. They have electrical lines. Some cities have subway systems. But all of them are supplied by energies and by energy, which is itself a network. So that's great. That's the physicality of the city. But now we come to what I said earlier in the introduction. There's a much deeper part of a city, and that's us. And that is the social networks of a city, the social network. So many of you recognize this kind of thing. Each node is a person, and those lines, the links are with their friends and so on. So this is a social network, and that's great. And you'll hear probably some talks about this here. But, and there's a great deal of work on the topology of this and understanding these networks and the structure of them and so on. The thing I want to emphasize are two things, which are not normally emphasized so much. The important thing for understanding how cities and social organizations work is what's flowing between people, not just the people, but what's actually being exchanged between them. That's one, and there's work on that. What there isn't work on is the following. We tend to think of this as some, especially now, it's sort of up there in the cloud. We have this sort of network that's somewhere in cyberspace, and we interact in this magic way. But of course, we have to remember that every interaction requires a person to be on a two-dimensional surface, sitting somewhere. You can't send a Twitter message or Facebook or check your email unless you're someplace. Could be on the toilet, could be in the kitchen, could be on the bus, could be walking up the street. You have to be someplace, which means that you are constrained by the network, the infrastructural network that is the city. So therefore, in terms of the complete dynamic, what the city is the integration between this kind of network and that network, which is the city in terms of its infrastructure. Because not only are you in some place, it is also necessary that you move, that you be transported. So that's that transport network, and you need to be supplied by energy, which comes through the infrastructural networks. The other aspect of these networks is that they are modular. We have modular structures in terms of our family, our businesses, our departments, whatever. But we have a regular modular structure, and Kimmo brought up Robin Dunbar earlier and quoted him. And indeed, this also, if you believe Dunbar's work, also has a kind of hierarchical regular structure in terms of its network, in terms of its modularity. And that plays very importantly in the theory, again, about which I won't be able to say very much. I just want to give you this big picture, impressionistic view. So the question is, do cities scale? Well, here's the mundane part of the city. It's the infrastructure, and here's a mundane thing, number of petrol stations versus size, and it's plotted in the same logarithmic way. And what you see is, yes, it's pretty good. This is 4 European countries, and it's pretty good. It looks like biology. The dotted line is linear, double the size of the city, twice as many petrol stations. No, not twice as many, obviously not, in fact. You need less than twice as many. You get an economy of scale, and that's what that slope being less than 1 is. The slope is not 3/4 like biology. It's closer to 0.85. So instead of 25% savings, every time you double the city, you only need 15% less than double number of petrol stations. But here's what's amazing. Turns out, as you can see by sight, it's not so different in different European countries. So we've looked at countries all across the globe, from China, Japan, to Chile and Portugal, I don't know, wherever we can get data. And it always looks like that, always about 15% savings every time you double on gas stations. So that's interesting. What is even more amazing is that you look at any infrastructure that you can measure, whether it's the length of all the roads, the length of the electrical lines, the water lines, whatever. It's exactly the same 15% savings. So there's kind of this universality of the scaling of all infrastructure within urban systems differing across the globe. So that's very interesting. That's very much like biology, except there's a 0.85 instead of 0.75. But as I mentioned, that's sort of the mundane part of a city, the much more interesting part, because it didn't exist on the planet until we became sedentary creatures and formed cities, beginning just a few thousand years ago. And maybe this didn't even exist in the universe before us, and that is all the socioeconomic activity. So here are 2 things here. On the left is wages. This happens to be the United States. Wages, and on the right is what's called super creative people, professional people like everybody in this room. And what you see, first of all, there's more variance, but you can see it's good evidence of scaling, and the slope is now bigger than 1. You never see this in biology. So instead of getting less per capita, economy of scale, you get more per capita. The bigger you are, the higher the wages per capita in a city. The more fancy, sexy people, powerful people there are in the city. The more innovative the city, to the same degree, I didn't put the numbers on there, the more patents produced in the city, also by this 15%. The more crime, another innovative phenomenon, by 15% in a city. The more police, the more taxes, the more fancy restaurants, etc., etc. And I'll just summarize it here. Here's a panel of just 6 different metrics in different parts of the world, showing, you can look by eye, different things, and they all have the same slope of about 1.15. There's this extraordinary universality, no matter what it is, that is socioeconomic across the globe, of socioeconomic activity. The good, the bad, and the ugly all come together, so that in English, so in mathematics, on average, if you double the size of a city, you systematically increase, on average, income, wealth, patents, colleges, creative people, police, AIDS, flu, crime, all of these things, all of them, good, bad, and ugly, all by about 15%, regardless of the size of the city. And You save 15% on all infrastructure. What an invention. You save on the infrastructure and you gain all these things, all this wealth and innovation and ideas, but also part of innovation is crime and disease. So that's the price, part of the price we pay. So the question then is, where in the hell does all this come from? Why is there this constraint? What is it that's universal about cities? And the universality, I've already basically told you, and it's obvious, is the universality is that cities are not there for their buildings and roads and the rest. They're there for things like this to happen. That's the fundamental reason for a city, is to have people sitting around, either, as you saw, in cafes, bullshitting and creating ideas, and most of which, almost all of which are useless and pointless. But every once in a while, one of those interactions produces quantum mechanics. Or Google. That's what happened. It's amazing, actually. So that's what cities are for. And it is the universality of social networks, the fact that this stuff is pretty much the same everywhere, because we are all the same. If you go to China, you can not only recognize Beijing or Shanghai as a city, but you can recognize the people in the streets as human beings, just like you. And if you were to emigrate to China, at a coarse-grained level, you would smoothly fit in. I was an immigrant to the United States from the United Kingdom. And, I have rough spots, but basically it's a smooth, on the coarse-grained level we're talking, we all interact, we're all the same, basically, at this level. So it's beautiful in a way. It's a representation of the unity and similarity of human beings and their dynamics. So here's that universality, just as an example. This is income, GDP, crime, and patents, all put on the same graph, renormalized. And you can see there's quite a bit of variance, because cities haven't been around very long, unlike elephants and whales and microbes. But you can see it's pretty damn good. And the question is how, this is science. There's a theory, which I, again, don't have time to tell you about, based on the network theory. But you don't have to know much of the theory to make a prediction. And science, as you well know, relies a great deal on being able to predict things and verify them or show that they're wrong. So there's a prediction you can make. If it's true that this all came from social networks, it would suggest that if I could measure how the number of interactions between people changes with city size, it should track this line, okay? So we've got to measure that. So in the old days, of course, we would go around and with a pad and ask people questions. Who did you talk to, and so on. And that's what social scientists did. Now, of course, we're very fortunate. Everybody carries around a cell phone, often a smartphone, and we're also fortunate that the telephone companies, probably for nefarious reasons, keep records of every single phone call you've ever made, and they know where you were and whom you called and how long you talked. Well, it turned out, fortunately, that we had a collaboration with our MIT colleagues, and one of whom I only discovered less than an hour ago is this young lady's, she's going to talk soon to be husband. I had no idea that Michael was just marvelous, wonderful. Anyway, he was part of this collaboration when he was at MIT. He's now in Budapest. We have these. So we were able to get the MIT had billions and billions. They were in cahoots with the telephone companies, and they had these billions and billions of phone calls recorded. So these were analyzed, and you did exactly what I said. You counted the number of interactions. That was quite an analysis. And by the way, an interaction was, I call Kimmo, and within 6 months you call me back. That defines a relationship that we have. So this is a proxy for social interactions, and you plot that versus city size. And, I'm sorry, that was not, what's happened? Oh, there it is, yes, there it is. So here it is. This is the number of those calls between people versus city size plotted in the same way, and there's two colors on here. One is Portugal, and one's United Kingdom. And you can see not only do they fall on top of one another, but they're parallel with this. They are just what was predicted. And because I'm running late, I'm not going to tell you some other very interesting things about this that you can discover about social interaction and the network. I'm going to miss this out. And I think I'm going to miss this out too, because I'm just going to say it, that you can also determine what the movement is. I'll just say it here very quickly. What the movement is of people in cities. And one of the things one can prove with this network, and a beautiful little theorem one can derive, based on some, obviously on some various assumptions about traveling, like people try to minimize travel time by going the quickest route on average. You can predict that if you take a region like here, just take this region around the CSH here, and you ask how many people are coming from 1 kilometer, 10 kilometers, 100 kilometers away, and how many are coming, from 100 kilometers away twice a year, how many people from 1 kilometer twice a week, or whatever, the frequency and the distance. You can prove they should go as an inverse of ridiculously simple law. And amazingly, this is just the data. This is, for example, this is data from, again, billions. This is big data. This is actually really big data. This is that quantity versus this R times F, the distance times the frequency, and it should go as an inverse square, and that dotted line is exactly the inverse square, and this is for Boston, Lisbon, Dakar in the Senegal, and Singapore in Singapore. And they all, you can see, it's just amazing that it fits. It's in fact, I'm not going to go into this any more detail. There's lots more of this, but I'll try to finish up as quick as I can here. I mentioned earlier the sublinear economy of scale nature of biological networks slows the pace of life down. Elephants move ponderously, mice scurry around. It turns out the superlinear behavior coming from social networks, which you can easily understand in words, because what is the nature of our social network? I talk to Kimmo, talks to Filippo, talk to her, Roberta talks to me, I talk to him, and we go around. And that's what was going on in that cafe. And we talk and we have this positive feedback mechanism, and that's how knowledge and science and general bullshit just builds up. So it just builds up more and more. It's positive feedback. So that's the superlinear. That's why it's bigger than 1, more per capita. And that leads to the increasing pace of life. The bigger you are, the faster everything goes. And so it's quite opposite to biology. I showed you this is the heart rate decreasing. This is hokey data taken 30 years ago on the speed of walking in cities. And we plotted it this way, and it's a lot of variance in it, but you can see it agrees pretty well with the prediction. And here's something whimsical. I saw this in a British newspaper about a year ago. What is here is the following. This is a picture from a street in Liverpool, England, and here's what the caption says. Research revealed almost half the nation, the United Kingdom, found the slow pace of high streets to be the biggest shopping bugbear. Bugbear means, the problem with them shopping. They were upset people walking too slow. So what did the city of Liverpool put in? A fast lane for walking. And this was the first day of the fast lane for walking because of this phenomenon. Okay, finally, I want to finish up with the growth equation. It's exactly the same conceptually as biology. The metabolic rate comes in. That's what comes in. It's much more complicated in a social system because you have to put everything in the same units, the ideas, the patents, the energy, and so on. I'm not going to go into that. But conceptually, it's the same. It goes to maintaining what's there, the buildings, the roads, all the maintenance, the hospitals. It has to maintain all the people. The hospitals and doctors are all part of maintenance of the people. So everything is maintained. And then it grows. It grows, develops new areas, grows new buildings, grows new people. And of course, nowadays, you would also add in immigrants, and you could put that in this. And that's what gave rise to this bounded growth. Slowing of the pace of life was biology. And that's, of course, a fundamental reason, by the way, that biology has been so sustainable for 3 billion years. Terrible for socioeconomic systems. However, if you take this and you put this into mathematics and solve it with the superlinear behavior of what's equivalent to social metabolic rate, if you like. Instead of this, this is what you get on the left. You get exactly what we see. I mean, exactly. We get what we see, superlinear unbounded growth, which is what we have. So it's very nice. It's very satisfying that the theory gives rise to superlinear behavior gives rise to super exponential growth, and I'm not going to show you data, agreement with the actual data, but you're familiar with it. But it has a built-in, this is where I want to finish up, it has a built-in fatal flaw. Not the theory, well, the theory might, but the system has in it a fatal flaw, and that's given by this dotted line, and that's called a finite time singularity in mathematics. And what it means is that this growth will become infinite. Whatever is plotted here becomes infinite in a finite time. Now, I remind you, exponential growth, the system becomes infinite, but you have to wait an infinite time. So in some ways, you could say, who gives a hell about infinite time? But here you have to care, because this says that something weird is happening. You can't have infinite wealth or infinite number of AIDS cases or patents produced. Obviously, it doesn't make any sense. In a finite time, in 5 years, 10 years, 100 years, but in some finite time. And the theory tells you what happens. It tells you that if you really insist on it, the system will collapse. So those familiar, it's a sophisticated version of the Malthusian argument that Malthus made 200 years ago about exponential growth. He was wrong, and most of the stuff that followed him was wrong along those lines. And I believe this is not wrong, but that's me. So the question is, how do we avoid this? And we know how we avoid it. If we go to this, so here's that graph, we're going along, we'd hit the finite time singularity, and we recognize that this was derived with a given paradigm, meaning the external conditions, so to speak, under which this growth took place were set in a certain sense. We just take that for granted. That is, it could be that growth during the Bronze Age, you discovered bronze and it made a huge change, or you discovered iron, or you discovered coal in the Industrial Revolution, or 50 years ago, or whatever it was, 30 years ago, we discovered personal computers. We invented personal computers. And 15 years ago, we stumbled into the internet and IT. And these are paradigm shifts, effectively, and they reset the clock, basically. What they do is they completely reset the clock. And so the idea is you come along here, if you continue towards this singularity, you would collapse. So you better make a major paradigm shift or innovation and start over again. You discover coal, and off you go, blah, 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 and so on. So you can just extrapolate this, and you have to just keep doing this, which is great. That's what we've done. Marvelous. We found our way out, and so on. But there's a problem. So that's good. But there's another fatal flaw in this system, and that is to remember that going along each one of these curves, going here, life is getting faster. So life is speeding up. That's already an issue. But worse than that, it turns out when you do the calculations, the time between these events has to get systematically and predictably shorter and shorter. So just to give an arbitrary made-up example, it might have taken 100 years to develop something 1,000 years ago. Now it takes 15 years. Would take, I mean, some analogous thing. And I will show you that in a moment. So this is a bit scary. And the question is this at all sustainable? That is, what it says is, yes, it's great. We've discovered IT and all this marvelous stuff is happening. But very soon, we're going to have to make another paradigm shift. Can't predict from this what it is. It may be it's driverless cars. It may be AI. It might be something that no one has yet conceived of, quite obviously. And that will start another one of these. But then in a time shorter than that, you've got to do another one, and you can make this reductio ad absurdum, so that every 6 months you're going to have to make some major, which is obviously nuts. So this is not sustainable, ultimately. I want to show you some data, and I will finish up. This is not mine. I have no idea who this is. I just found this graph on the web. And it's no relation to mine as far as I know, but he's done it that way. And what this is showing this, and it turns out these numbers, what this is, he's taken each one of these modern inventions and asked how long did each one take to get 10 million customers. Sort of an interesting way of parameterizing. I don't know how seriously you should take it. But actually, if you take these numbers, it fits exactly the prediction of what I did. But more significantly, maybe, this is also not mine, although I've redrawn it, is this is this person many of you, I'm sure, have heard about, Kurzweil, Ray Kurzweil, who has built the whole thing on singularities and the idea that the next singularity is going to be, you know, we become gods, or then machines take over, whatever. I don't know. To me, luckily, I'll be dead. So, but here's the graph he had. Here's the graph he has, and let me just take 1 minute to explain. This is how long it took to develop whatever it is. So primitive cells took almost 10 to the 9th years to develop, and it happened over 1 billion, 10 to the 9th years ago, okay, and so on. So, and so forth. You get it? This is how long ago it happened, how long it took, some enormous time then, and an enormous time ago. And as you come in here, it takes almost no time to create these things, and it just happened. So plotting it logarithmically, it stretches it all out, and you can see it. What is nice about this is, even though I don't really believe this, that straight line is what this theory predicts, exactly that straight line. So I think I had a whole section here, but 48 minutes, not bad, 48 minutes. A bit long, but not bad. I had another section, which I'm not going to talk about, is companies and diversity and where companies fit and why companies die, and showing you data that all companies do die. And this is very much work in progress, and the scaling of companies, and they scale in a very interesting way, somewhere between cities and organisms. You know, the idea there is, can you in fact get a kind of a similar kind of, so let me just back off a second. The stuff in biology is very well developed. There's now, you know, there's a whole body of work, many issues have been addressed. Once you have a theory, we can understand questions of sleep that I mentioned earlier, and aging and so on. The stuff on cities is reasonably well developed, but it's still very much a work in progress. It's not, the theory is not on the same basis quite, I would say, but it's very similar. The stuff on companies, I'm not even showing you the data, is still very much work to be done. We have good phenomenology and so forth, and it's based on examining the records of all 30,000 US publicly traded companies from 1950 until actually 2014. So we have all of those and all of their data. And that's been very illuminating, and it does show that essentially all companies die. And the idea is to get a theory and to see, die, by the way, I do have to change say one thing. Die here has a slightly different interpretation. Die does mean, of course, liquidation and bankruptcy, so the company just goes completely out of existence. But you know, most companies don't. Most companies go into mergers or are bought up by another company. But we call that death, and it's called death in the literature, by the way. And it turns out, just as a side comment, the phenomenology of the mortality of companies that die, literally, sort of biologically die, is almost identical. You can't tell the difference to those that have been lost to mergers and acquisitions. But anyway, the idea is, can you get a theory that you can then have a coarse-grained description of not just understand this, but predict when, you know, there'll no longer be a Google or a Microsoft, because eventually they would disappear, like everything else, or Walmart and so on. So let me hold it. I'm going to go. I'm just going to. I'm sorry. I just can't. I just want to show one thing, because this is great stuff, actually. I want to do two things, and I finish up 2 slides. First, I didn't say it, but if you were alert, you would have noticed that your metabolic rate on that graph of metabolic rate, biologically, is less than 100 watts. you operate, the 2,000 food calories you eat a day, if you do the little calculation, is 90 watts actually. So you're like one of these light bulbs. So we are unbelievably efficient as organisms. We're incredibly efficient. However, if you ask what is our social metabolic rate, that is how much energy does each person in this room, well, I should be careful here, I don't know the United States. If it were in the United States, each person in the United States need to live the life he or she lives, you know, with the buildings and the cars and the roads and refrigerators and IT and so on. It's not 90 watts, it's what I've written there, 11,000 watts, which is extraordinary. 100 times, more than 100 times bigger. That's equivalent to, you can turn it around and ask how big an animal is each one person in this room, roughly, where each one in this room is acting as if we're a 30,000 kilogram gorilla, or each one of us is about a dozen elephants. There are 7.5 billion people on this planet now, and it's going to 10 or 12 billion. And each one, roughly speaking, modulated with culture and geography, wants to be like us, meaning they want to live at this standard of living. I don't care what, I mean, I know this may not be politically correct to say, but I believe it true. Each person, given the opportunity, would like to have all the extraordinary things everybody in this room has access to, which means we're going to operate 100 times faster. And this is just unbelievable. You know, this is just crazy, actually, in my opinion. Okay, so I cannot resist, because of my own ego and narcissism, showing you this. This, because you mentioned already, is if you want to know more, it's in this. Wait, this book. So I will finish there, and I'm sorry I went on for too long, but okay. Thank you.
Hello. You gave a lot of examples from mostly mammals in biology,
Yeah.
And I would be very curious to hear about other classes like plants or fungi and stuff like that. And I just had a question in mind. I mean, probably it's been looked into, but I don't have much idea. But would trying to resemble those systems when we build things instead of mammals be an answer to sustainability? And yeah, I'm just curious.
Yeah. So first, I didn't say, because this talk was, the biology was just in there to present the background and lead into the other stuff. No, it's the same, first of all, in terms of the data, the same scaling laws occur at the cellular level, at the plant level, at the fish level, bird, all of them work. And I didn't show you, but there's all the theory applies, and it's very important that it does, because we have our network, our circulatory system, for example, is a bunch of tubes, right, joined together. But the tree is a bunch of fibers, right, that join, and it sprays out like an electrical cable. And it has no beating heart, doesn't have a beating heart pulse. And so the theory, the same underlying principles, which I didn't have time to go into, when applied to plants, also give rise to the same scaling laws. And in fact, we're amazingly similar to plants, despite the obvious differences. So yes, you can. In answer to all of that, it permeates across essentially all biology at all scales. The question as to can you take it into cities and socioeconomic systems, the answer is partially yes, because, I mean, that's the question. Can you use that to somehow start speculating about what we can do to avoid potential collapse? I mean, maybe this is all wrong. I mean, maybe what I said, my speculations about extrapolating it into the future it may be wrong. But one thing you immediately see is that if you had some analog to economy of scale, something like that, or you redefine growth in some way, maybe you could do it. And you know, I don't think you can do it by just copying biology. I think that's not possible. I mean, copying biology you can do, because we did for most of our existence. You know, just go back to being hunter-gatherers, which worked presumably quite well, very well. But if you want to have all this, that's the issue, right? And I don't see any way of doing that unless we start to redefine the terms of what we're discussing. And in particular, if you believe that underlying it is social dynamics, then it's fundamental, something fundamental has to change in our social network structures and our social dynamics, which means almost a cultural revolution. And which makes me very pessimistic that I just don't see that happening. I mean, we've seen bits and pieces happen. Actually, you know, can I take 1 minute to just say something to that? Because one of the things, you know, I got more and more depressed with President Trump because he was a reaction to this kind of stuff, obviously. I mean, it's a throwback to kind of Neanderthal thinking, so to speak. You know, he doesn't believe in science, doesn't believe in truth, doesn't believe in continuity, and so on. But on reflection, I realized that the one hope I have is given to me by Trump, because Trump was able to do something in less than a year, something extraordinary. He got, you know, the United States population to accept that you don't need facts, you don't need science, you don't need to be truthful. It doesn't matter. You know, well, we can just speak your mind. Doesn't matter, whatever comes into your mind. That is extraordinary. I mean, to have that change after, you know, we've had the Enlightenment, we've had the Industrial Revolution, and so on. And suddenly, in less than a year, people are willing to just chuck it all out and think that it's all going to be great. That is extraordinary. So that, I realized, was the clue. What we need is an anti-Trump, someone like Trump, but has exactly the opposite views. That is, believes in, you know, humanity, and believes in science, believes in truth, believes in love, believes in so on. And sort of a kind of a version of that is a Trump version that has the power of a Gandhi or a Martin Luther King or someone that can somehow irrationally change people for the good. It's totally naive what I'm saying, but it's the only, I don't see any other way, frankly, because it needs a fundamental cultural change. And if Trump persists, of course it may just be a year or two, he may collapse. I mean, I actually believe he will collapse. But if it sustains itself, then, and it is a serious shift, it is a phenomenon that is truly extraordinary, and we should understand that dynamic, and maybe someone will come along that will be our savior.